Okay, hi everyone. For people who are joining this live stream, we are continuing to talk about template reactions, and supposedly we're talking about chemistry, but actually we have a number of people here because we're really talking about graph rewriting, and chemistry is just an instance of graph rewriting that happens to apply to things that really exist in the world, and it's also related, I think, to things about pattern to pattern rules and things like this. So let's try to remember, can we remind ourselves where we were before? We were talking about how to represent the dummy elements of molecules, the functional groups that are often written as R and R prime and so on. Now, I had some notes from last time. Was it down here or? Oh no, where are my notes from last time about I had a bunch of those notes where I had found examples of template reactions that other people had written down. I think we should have had those for this. That's in that was from April 14th. Let me try and use those. Okay, here. These were our examples. R prime, R double prime, all these kinds of things, right? Right?
Yes.
Okay.
Yes.
Okay, so do we think so what we had discovered there was that there is this slightly funky notation, but that fundamentally there are, yeah, go ahead. What are you going to say? Please. Go on. Have you made further progress beyond this? Yeah, go ahead.
So I have not made very much progress here. I mean, it mainly removed the stuff about atom map numbers goes to whatnot. But I feel like we're at a pretty. We need to nail down exactly what input forms we accept before I can really make more progress. And we need to nail that down so I can.
Yeah, I know. We need to do it now.
And Jason and I had various discussions afterwards, and I am actually a little bit concerned with this suggestion of R underbar, because it loses the information which R it is. It is the same R, but not in the sense of R underbar. It is the same R in the sense of lowercase r underbar uppercase R. Versus lowercase s underbar uppercase R. And like I feel like we didn't get this right the last time.
Okay, well, explain that. I mean, you're saying, look, the thing that's weird
the R's is not the same. There are different R's. They look the same, but there are different instances of it.
Okay, so
we must account of them independently.
Why is it, Michael, that we always end up with this epistemological, whatever, ontological? Your point is, just because this is an R prime, these are actually different atoms here.
Yes. And which one is where on the right-hand side is lost in the R, but is preserved with the index.
Okay, but so the bizarre thing that you're pointing out is that the two functional groups might both be, and I'm going to make up chemistry, I don't know, hydroxyls or something. They might both be OHs or something like that. But your point is it's a different oxygen atom and a different hydrogen atom, even though the template of the radical is the same.
That's not quite my point. That's 50% of it. The other 50% is that and it's not visible in your right-hand notebook, that there is an index on them, and the index is what matters. They are not interchangeable. Like if you would isotope tag one of them, then you would run into a trouble.
I understand because there's an actual carbon atom, and you're saying that actual, quantum mechanics be damned, that actual carbon atom winds up in a particular place on the right-hand side of the reaction.
Exactly. That's why just having an R underbar on the left-hand side is underspecifying the problem compared with having an index.
Okay. Can we understand, for expressions, oh my gosh. I mean,
for expressions, this doesn't matter because there's no conservation law. We can, if it's an R underbar on the left side, we can have 5 R's on the right side without trouble.
mean, there's a lot of stuff you can do in a regular in a normal Wolfram language expression with patterns. A lot, like it's a very. I don't need to tell you that.
Right, but so you're saying when it's physicalized and there's actually an atom in the physical sense of an atom, boy. And you know what else is confusing? And confusing to me is in our physics project, right? Atoms of space also can be replicated, like unlike physical atoms. So sorry, that was a side comment for Nick and people who are into that stuff. Go ahead. I mean,
well, so let's see. So just to back up just a little bit, if you go over to the notebook on the left and scroll up just a touch, I've put two basic input form. I mean, well, so there's 3 input forms, and none of them has the atom map number goes to this. In the first form, you have a list of pattern objects goes to a list of patterns, and then you specify the mapping with an association as a second argument.
I see.
And I think
that way of doing it is a part number based. Is that correct? I mean, that 1 means the left-hand side of the reaction. I don't quite understand now. What is this? This is atom 1
of reactant 1. Yeah.
Right, because we've already numbering the atoms here for the bond specifications.
Yes.
Now, let me understand something else. In our graph data structure, and this is really a question for Charles or somebody else, we have the possibility of saying graph of vertex, comma, edges, right? Vertices, comma, edges. But the edges refer to vertices by the explicit names that the vertices are given in the vertex list, not by their indices in the vertex list. Is that a correct statement?
Yes.
Okay. So we don't have a pattern. So
no, wait a minute. I think that the question is not quite sensible, because it's an atomic object. So without having applied an extractor, the question makes no operational sense.
All right, fine. I mean, I mean, the thing that we're doing here. So what we're seeing here is we've got a list of atoms here, and we're referring to those atoms by their positions. Now, presumably, we could, and maybe you support this, maybe you don't yet, we could have in a molecule pattern, we could have this be an association, that list of atoms there. If that was an association, we could name the atoms with us, but for purposes of the bonds and for these purposes here. And that might be convenient.
So one goes, or the lowercase string c goes to uppercase string c.
For example, but I mean, let's say, and again, maybe this is just not something people do. And I mean, I could imagine something where we say here an association, and we say, you know, center goes to C, and then, you know, R1 goes to O, R2 goes to O, and then here we would say, you know, center, you know, R1, etc.
Yes, absolutely. That would be very convenient. The only the reason we didn't go that way is, I mean, just that, let's see, when you go to then combine molecules or break them apart, do you keep those associations or do you not? I mean, when you create a molecule from a smile stream.
Okay, that's welcome to the world of graphs, right? We've got the same exact issue with graphs. So in graphs, if you do a graph union, we're using the names of the vertices to decide what to union with what, right? In this case, one of the things that would happen is, what if there are two, you know, you're combining a molecule that has an atom labeled the center with another molecule which also has an atom labeled with center. Well, that's the same thing as combining two associations, and there are a variety of different ways to do that. Can anybody comment on what the most sensible way to do it in this case would be?
In graph disjoint union, it first calls graph renumber, I think is the function, to renumber all the vertices and the edges.
I thought it's index, isn't it index graph that gives you a renumbered graph?
Yes, it calls index graph. That's what it does. And then it can do the union without losing anything because it increments the index from for each graph that's input so that there's no overlap.
By the way, does index graph have an option to determine what the first index is? Charles?
It's its second
yes,
argument. Or
second
something.
argument.
Okay, very nice. Okay, but so then here,
So you definitely
Okay.
could imagine entering the first argument of a molecule as an association, but that is not.
okay, fine. But I'm just trying to conceptually understand what's going on here. But most of the time, we are sort of atoms have positions. Atoms have indices. Those are the indices that we're referring to here with the bonds. And in this case here, we are describing the reaction. I think this is a sensible way to do it. I have to say, I think this is because among other things, that would allow you to take that object there, presumably, and that object becomes some kind of, I mean, that's telling you the mapping. It's got to tell you the mapping of every atom to every other atom. Although sometimes, as you've told me before, atoms can get lost.
Right. If the user wants them, if the user wants to discard the unneeded parts.
Right. But so, yeah, go ahead.
And while not in the same meaning, structural, this is exactly what we do for multi-stranded biosequences, where we have strand, and then we have the indices take base 12 from strand 4, connect with base 3 from strand 19.
Right, I remember, yes. And that's done in Biosequence. How do we represent a composite biosequence? Is it?
Usually, we provide a list of biosequences of the basic types like DNA or peptide in the first argument.
Okay, and then we have a second argument, which is the mappings.
The bond, that will be the bonds actually. Give the indices of what connects
Okay,
to
so
what.
it's a third argument. Well, it's a hybrid strand.
Sorry, third. Yes, third.
Okay,
Hybrid
so
strand is different from sequence collection.
Okay, but so in this case where there's bond, that is a list of, that's a list. Let me just understand that. That is a hybrid strands. Okay, so now where does it say? Okay, so here, that means that the A on here.
Yes.
I'm confused here.
To the U of the second one. So the
Right,
first.
I understand.
Yeah.
But now, if I had a great big zippered, whatever it is, a great big thing with connections all down it, would I have a single bond with a big long list of hydrogen, these hydrogen bond connections, or what would I have here?
No, the design we decided on is that you'd have to enumerate each of the bonds. I think there's an example somewhere down below. One of the large models.
Well, I don't know, where does? Well, so wait a minute. So you're saying that in a single bond here, I'm a little bit confused about the
It's
chemistry.
actually base pair. Bond is a base pair.
Yes.
And there's
No, and I
list of
understand that's bonding to two elements, two bases in a base pair.
Yeah, but the design was that each bond is separate. You cannot. There's no list of bonds inside. That's the design, which was decided.
So wait a minute. So separate base pairs correspond to different bonds in the list. Is that correct?
Yeah.
But what's this? What's that creature there? With the four things in it. Is that I don't understand this at all.
Yeah, so in the first component, the second base, which is A, is connected to the fourth element of the first component, which is your T. That's why 1, 2, which is indexed as 1, 2, and 1, 4.
So this is a bond within that first strand, is that correct?
Yes, right.
And so what does this mean here?
That's because this is what we called an inside bond representation. In here, the bond is put inside the biosequence within hybrid strand. The one before that is the external bond representation. So those are equivalent ways to look at things, because there are operations that are easier when the bond is within the component as opposed to being outside the components.
Okay,
but those are supposed to be equivalent representations.
So here's a question. I mean, a bond is this relationship between atoms in a static molecule. In some sense, in space-time, these things here are similar kinds of, they're kind of like bonds, but in space-time. Does that make any sense? A bond is a spatial slice, right? Of, you've got two atoms, and maybe they're at, super high frequency. They're exchanging electrons or something. If I'm understanding anything about this chemistry, which I might not be, but you can think of maybe that way.
Sure.
But what you're imagining for a bond is you're freezing it. You're ignoring time, and you're saying spatially these two things are being connected by this thing that's bouncing backwards and forwards in time. Okay. Now a reaction happens, and if we looked at the space-time diagram of where those atoms wind up in the reaction, we would see that the atoms, move from one place to another. They move in space-time. There's a space-time, there's a world line for each atom. And so I'm just trying to understand the analogy. I mean, in a sense,
maybe not quite. Like, you could literally imagine two say H2s together, parallel aligned, and now you flip the bonds. So they wouldn't have to move to still flip the bonds.
Fair enough. But I think the thing you're trying to capture here is which atom winds up being which atom of the product, right? Which atom of the initial state ends up at which atom of the final state. And that, to me, is kind of like a space-time bond. Or am I completely confused?
I think it's mostly time. Space can be ignored for it, I think, for all practical purposes.
So basically, it's a before and after situation. After the reaction happens, the atoms may or may not be connected anymore.
No, I understand that. But what I'm saying is the concept of a bond is, and maybe I'm confused here, but somehow I'm just seeing this as being kind of this idea of a bond, which we're representing here. I mean, here's the question that I'm trying to ask. These arrow notation may be the right thing, but I could also imagine a kind of what would you name when you say this atom in the initial state goes to this atom in the final state? What would you name the relationship between those atoms? What is the relationship between those atoms? What's that called in chemistry?
Conservation of mass, usually, because we.
No, I understand. That's the phenomenon.
Oh,
but what I'm asking is, you say there is a chemical reaction, okay? And there must be, because I'm learning as this analogy between particle physics and chemistry, there must be exchange reactions where this is kind of a joke that it should be possible to infer something about chemistry from particle physics, but where there is an atom that sits on one molecule, and then in the reaction it is exchanged with an atom that that the atom's in two places, and somehow they can be exchanged in the reaction. Is that a true statement?
Yeah, but I don't know that there's necessarily a that you tend to think of it in the terms of looking at the before and after and identifying the relationship between those two atoms, which you can. I mean, you think these are the same atom, like they are. That's what you think when you're at least in learning about these things.
But wait a minute, when you exchange the atoms, if they're fermions, for example, it matters. Or am I confused?
Well, so I guess I was thinking that you were exchanging non-equivalent atoms. That you had, like, one guy had a chloride.
No, I'm saying you exchange. Is it the case that you can exchange two identical carbon atoms, and that you can recognize that carbon atom number 1 went to position 2, carbon atom number 2 went to position 1?
I mean, only if you usually you tag. So let's see, they do exchange atoms. Like I assume that
Right,
they
you tag
exchange
them with
hydrogens.
isotopes.
Right.
Yeah.
Yeah.
But do you care about that? Would you represent that here, or would you not represent that here?
I don't think that you would.
So you would
I mean,
just pretend that those were identical carbons.
I mean, unless you were specifically studying isotopic labeling experiments, then you usually wouldn't care.
Yeah,
Okay,
and
but-
isotopic labeling is important.
No, I
Yeah.
understand that. But I mean, when we have a template reaction, some standard template reaction, you know, in truth, if somebody had done an isotopically labeled version of that reaction, they would know whether those carbons exchanged. But are we going to record that or not?
It often doesn't get recorded unless there's a need to understand in depth the mechanism. Yeah. So oftentimes, if you end up with the right product, and that
You just
product
don't
is,
care.
it gets ignored.
Okay, fine. But I mean, I'm just asking, in the database that we're going to build up of template reactions, we are not going to care about that probably, unless somebody happens to have an isotopically labeled, unless somebody happens to have derived one of these reactions in an isotopically labeled way.
well, let's see.
I intend to model biosynthesis using labeled isotopes, isotopically labeled reactants, and follow their course through a series of reactions to see where they end up, not just position-wise, the regiochemistry, but also the stereochemistry. I mean, that's what I did my graduate work on, and I'd really like to be able to turn that into a computational machine so we could apply it in a general way to study the biosynthesis.
Okay, so you would like to have our template reactions actually take account of, so we would end up with a mapping here where the left and right hand sides are both carbon atoms, and well, I mean, in all cases here, I'm so confused with this. In all cases here, the atom type on the left hand side is the same as the atom type on the right hand side, correct?
Yes.
Better be the case.
And so we
Alchemists didn't make it. Go ahead.
Well, I mean, so it's, let's see. So we keep, even though these carbon atoms, we might think of them as equivalent, and when you just want the products back, you lose the mapping number, like you lose the history of it. But we do need this mapping here in order to do the stitching up, so that the carbon that was labeled number 3 on the left, it had some dangling. It was attached to some parts of the molecule that were not part of the template. And so they get carried along. And so these mapping numbers are what allow us to carry the things along.
And there's no stereochemistry information that you need. You just need the mapping. You just need this atom goes to this other atom. There's no. Go ahead.
We do need, in general, stereo. Like, so in general, we carry the stereo over from the reactants to the products. Like what you feed in gets carried over. We need to expand molecule pattern to account for stereo, so that we can then have reactions that change stereo. But we don't have that at the moment. The way it'll work, there's an option for molecules that specifies stereochemistry, and so we'll be adding that to molecule pattern.
Okay, but does that affect these transformations, the stereochemistry? I mean, can one of these involve twisting something that like that atom has certain bonds on it, and this side, could those bonds be twisted or something?
Yes, I believe so. So you can definitely write these template reactions to do things that would not necessarily be physical. Like if you write that, you know, you had a carbon atom over here that with things arranged around it in a specific stereochemistry spatial way, and then it gets brought over into the products and things get completely rearranged because you took the trouble to write them out that way. And it might not correspond to like an elementary step in a reaction.
Okay.
Yeah, it's the result of several steps, right, Jason?
That's how I
in a mechanism. Yeah. And stereochemistry can also be generated de novo, especially in ring forming reactions.
Okay.
Rings can only twist a certain way, and that because the other way would result in something very strange and unstable.
Okay. So look, this design seems like it is the least crazy of the things we've talked about. I'm not sure if this should be an association or just a list here. I kind of think it should just be a list. What do other people think?
Jason brought up one strong argument for the association. You don't make the mistakes by having a left-hand side key twice, because you can only use it once.
Yeah, so that occurred, but it doesn't stop you from using the same
key on the right-hand side.
Yes, and so both need to be checked.
I think it's a hack. I don't know if other people have an opinion about this, but I think it should just be a list. I don't think the meaning is right for it to be an association.
Okay.
No, that's good.
And okay, so then the reaction here. Okay, so let's just understand the form here. So we've got a list of molecules, arrow a list of molecules, and then here we have, in a sense, the transpose of that, where we say atom goes to atom. Here we've got molecules goes to molecules, and this is essentially the atom by atom version of this. It's the transpose of this thing. Here we've got a list of atoms going to a list of atoms, and here we've got the list of individual atom transformations. Am I right?
Yes.
Okay.
Yep.
Okay. I mean, I guess
it's kind of like a sparse form of a permutation matrix.
Yes. And the way we're referring to the atoms is always which molecule number in the molecule pattern. By the way, I assume that in this left-hand side, we could have just a plain molecule here, not a molecule pattern. Or am I confused? Why does this have to be
I would assume that so the question then would be, so if you put in a molecule of ethane, does it match only pure ethane? Or so does it match C2H6, or does it match any C2? And so I think it would have to match just the first. And so it would be.
Let's give an analogy with strings. Okay, with strings, that if we do a string transformation that says A B goes to blah, that string transformation in string replace is that substring anywhere in the string, right? As opposed to a whole string replace, which we could also do by anchoring things in the string pattern.
Right.
But in this case, I mean, you're saying in this case, a molecule pattern means this is a subpart of a molecule with all kinds of things hanging off it, whereas molecule would be it's that particular molecule.
Yes.
Correct?
Yep.
I would imagine. Go ahead.
That's what we've been assuming all along.
Okay, but I mean that really matters in these reactions, right? I mean,
you might want a reaction where one of the parts is a specific molecule. It has to be that and only that.
Okay, so let me understand. When you write this thing here, how does that get written out in these terms? What are these R things? How are they specified? Are they just? I'm confused here.
So in a molecule pattern, you would write either underscore or the string with an asterisk. R, do not have a defined semantic meaning to R at the moment because it gets used in a lot of different situations and not always following the same convention. So I haven't wanted to. So I've resisted nailing down exactly what we mean by R. But yeah.
Could we talk about this name chemical template reaction and whether it should be called chemical transformation?
Right. So I put a note at the top. I mean, I think of it as an object that acts to transform lists of molecules. And so I thought maybe molecule transformation, although chemical transformation would work as well. But the point being that it operates on a list rather than necessarily just one. Although it could obviously take just one if and then normalizes.
What do you mean it takes just one? It takes one if it's some molecule it's falling that it just happens to be a single a single unimolecular, right? A single connected thing on the left goes to something else,
right? but in the general form is that it transforms a list of things into a list of things.
Okay, so chemical reaction, let's remind ourselves what that is. Chemical reaction would have the exact same form as this. Or this is the, I'm confused. This is, go ahead.
So chemical reaction came out in the previous version. It takes a list, arrow list, but the things inside the list can be a chemical formula or an entity, or any of the.
So I don't understand. Why is this a different function? Why isn't this just chemical reaction?
Let's see. So chemical reaction doesn't contain any transformation information. It allows you to just write. You can write a chemical reaction with just the formulas.
So
you already know the reactants and products explicitly. You're not allowing the machine to compute the products for you.
Yeah, they're definite already.
So what? I mean, I don't understand. Isn't that in this particular case here? You're saying that there's no reaction apply for a chemical reaction. That is, a chemical reaction just is what it is with literals.
Right.
Yes.
Yeah. And also a chemical reaction, let's see. So you can put stoichiometric coefficients in front of things, 2 waters and such. But
how do we do that? How do we do that?
So either through the string inputs or through an association.
Okay, why do you not need stoichiometric information here?
Because if you have 3 different water molecules in your template reaction, then they are going to end up in 3 distinct places on the right-hand side, and so they need to have their own.
You must account for everybody where they end up.
Yes.
I thought you didn't need to account for things. I thought things could just go poof into the solvent and things like that.
Exactly.
That's
why we don't use reaction.
But okay, so let's ignore water. Let's say you had 2 glucose molecules that you were sticking together to make a disaccharide.
Mm-hmm.
Okay, you can't say 2 times glucose or 2 copies of glucose goes into the reaction because of the atom mapping and stuff. You've got to say which one is the one on the left and which is the one on the right, because the connection is made between different atoms in them.
Okay, if it matters. I mean, but if they were a bunch of identical things, couldn't you have something where you have, I don't know, making some mineral, for example? You could have, 3 aluminums plus something or other, plus 2 irons or something, goes to whatever.
Right, and in chemical reaction, the detailed arrangement of the atoms in the reactants and the products is completely ignored, whereas in what we've been calling template reaction or reaction apply, that detail is paramount.
Yes.
Oh my gosh, this is a mess. Sorry.
It is complicated, but so the template reaction is useful for when you want to create molecules that you're not even aware of.
I understand. I understand. Chemical reaction is a literal, unpatterned transformation. Now, you could imagine, okay, if there were spectators in a chemical reaction, I could imagine something where you apply a chemical reaction to some collection of molecules that includes some random spectator molecules, and it will pick out of, you've got, I don't know what, hydrochloric acid and sodium. I don't know anything about chemistry.
Sodium hydroxide.
Sodium hydroxide is what you're looking for.
Yes, that's right. And it makes a big fizzing thing. Okay. But you also happen to have some random sodium chloride lying around, which the chemical reaction does not pick up because but you could perfectly well imagine something where you've got those spectators there.
Right, and that would be an equilibrium problem because you would have to worry about the forward reaction between the HCl and the sodium hydroxide, and then the sodium chloride reacting in the other way. That would be a different container and sort of a layer up above a template reaction.
But why isn't that a chemical reaction? Why isn't that something where you've got the chemical reaction between the hydrochloric acid and the sodium hydroxide, and then, and that's defining a chemical reaction? But nevertheless, there's a chemical I don't know what we call it, a chemical state that contains what we could perfectly well define the stoichiometry of, something with some number of sodium chloride molecules there and so on. And then we could say, okay, is there a version of a sort of chemical state onto which chemical reaction is applied? Does that even make any sense? Isn't that what limiting reagents and things like that are all about? Of you have to have some number of this kind of atom, this kind of molecule to, isn't that? I mean,
so I think chemical solution is the thing that we want to address next in the next. So right now we're trying to do a chemical instance where you can describe 3 grams of sodium chloride or 3 grams of sodium chloride at 20 degrees C. But next will be chemical solution, or a more general term would be chemical mixture. But
chemical mixture sounds much better than chemical solution.
Right, but they're distinct and not the same, right? I mean, a solution is not a mixture. Is that right, Jason?
No, all solutions are mixture. All mixtures are not solutions.
Okay. Then, so a chemical mixture.
The definition, I'm sorry, the definition of a solution is that there is some chemical binding between, or what does it mean? What does solution mean?
It has to do with their degree of mixing, right, Jason?
Yeah.
And phases. So
phases, yeah.
You can't distinguish them anymore.
Right. The salt and water, you get one collective phase, whereas when you start the mixture, you have a solid sodium chloride and liquid water.
Okay, so there's spatial distinction in one case, whereas in the other case, it is spatially all mixed up.
Correct.
Yes.
So in other words, if you have lumps of salt in there, then you would still call that a mixture, although how on earth are we going to represent that? I mean, don't you need to know how big the lumps are and stuff like this?
Well, that gets back to the equilibrium. If you have the amounts in the equilibrium constant, then you can compute all that, actually.
Yeah.
Yeah, we just wouldn't count the lumps of it.
I don't understand. How could you compute it? I mean,
I don't know that we could compute the size of the lumps.
No, we couldn't. That's right. We couldn't compute the size of the lumps, but we could tell you how much is in. So if you have more salt in the mixture than could actually go into solution, we could figure out what would be left over.
How many grams? How many moles?
Right. We wouldn't be able to say that they form 3 balls of this size or 2 squares of that size.
No, I mean, honestly, I don't think. I think mixture, unless it has some bizarre chemical meaning where random things are precipitated out of the solution and things like that. I mean, it seems like a much. Well, okay. Is it the case that whenever you mix, okay, if you mix chemicals together, I mean, if I take xenon and krypton or something, and I put them together in a box, is that a solution?
What temperature?
They don't interact.
Temperature.
What's that?
What temperature?
Well,
I don't know, but I mean, it's a temperature where they're not interacting.
I mean, assume they're both gases, right?
Both gases.
They'll diffuse into each other, so it counts basically as a solution.
That would be my understanding as well.
Okay,
so
if
it's a gas solution.
Right. So if it's all the way down to the molecules, it counts as a solution. Is that what you're saying? If it's ground all the way down to the molecules, it counts as a solution. If there are bigger lumps where you have little pieces of one, little regions, spatial regions of one type of molecule and another type of molecule, then it counts as a mixture. Is that right?
If those regions are actually a solid phase.
Right. Well, so I mean, there's going to be some kind of, the word homogeneity is going to come into the real definition.
Yeah.
I don't understand. If you have a little oil in water, for example, where there are droplets, right?
Not a solution.
That's not a solution.
It's a mixture.
Okay. Yeah. Because you can distinguish the oil and the water.
Yeah, right. So the solution means it's ground down to individual molecules, and every other molecule could be a different molecule, so to speak. Whereas a mixture is something where there are bigger lumps of one kind of molecule. Is that a correct definition?
It works for me.
Yeah, pretty much. And a lump could be a liquid droplet, or it could be an amorphous solid, or it could be a crystalline solid.
Okay, fine. But it is something which, even though it might be quite small, it is something which can be an identifiable phase of that material.
Yes, and you could physically separate it.
Okay. All right. But anyway, so what we've got here is a chemical reaction. Oh my gosh, what is this? see a chemical reaction, presumably we have reaction constants and things like that, rate constants and things like that we might put into the chemical reaction. Is that a true statement?
Absolutely. So the idea there would be to extend it to have another argument that would be an association, which could take things like rate constants, things like temperature, right? So reaction conditions, agents, or let's see, non-reacting species.
Well, that's good. So catalysts, for example.
Right.
Where would that go?
Well, so in that association would be, I don't know if catalyst covers all types of non-reacting species. I mean, catalyst has a specific meaning, as in like it speeds up the reaction, but they would fall into that category. And so chemical reaction would take an association of annotations is what I like to think of them.
Okay, fair enough. But so, okay, fine. So there's chemical reaction, and that's distinct from, which is of particular molecules where we know what the molecules are.
Right.
Yes.
And potentially the left-hand side of a chemical reaction is what you're calling a solution, rather than, let's see, well, you say reactants here. Reactants may be given in this form. Okay, reactants to products. So this left-hand side, which is usually a list, could also be a chemical solution with certain percentages or something of the different molecules. Is that right?
Yes. I mean, when we introduce that data type, then yeah, absolutely, that would be it.
What's the relationship between? Okay, reactant counts. So here, I'm confused. If we say 2 H2Os and 3, you don't describe that in the documentation up here. Growl, growl. It appears down here, but it is not described up here. Growl, growl. Sorry, I'm sorry. It is. It's right here. Excuse me.
No, I mean, I'm guilty of it sounded like me, so I was willing to believe it.
Right. Okay. Well, anyway, it is there. Although it might be nice to show that as a table. But okay. So then here, so this, when you say 1 zinc hydroxide and 1 hydrogen chloride, I could as well put that in a chemical solution. Is that right?
I think here you would want to use chemical instance, not a solution.
Well,
why? Why? Because it's going to react, or what? I'm confused. Does chemical solution have to be something that is non-reacting? What's the difference between the left-hand side of a chemical reaction and a chemical solution?
Do you know the solvent?
Well, I think we should say chemical mixture, because solution
chemical mixture,
a solvent. So I would think that when we have a chemical mixture as an object, that you could definitely put it in any place where you would put a list of chemical objects.
You mean, or an associate? But this, in the list of chemicals here, are they of unknown concentration, or are they of equal concentration in that case?
The concentration doesn't matter here, because the chemical reaction goes in terms of numbers of particles. So you can write it in, you need 3 waters plus 4 of something else to make 5 of the thing on the other side. So technically you're working in moles, individual moles or molecules.
No, I understand, but in this form here, where you've just got a list of chemicals, doesn't it matter that there are twice as many waters as there are something else's? And you're not giving that information here.
Right. I mean, so that's I essentially call counts on that to turn it into the other form.
Oh, I see. So in other words, if there were 2 waters, you actually have to have waters listed twice in that list of chemicals.
Yes.
So that's the individual. You need to make this documentation better, but that's the individual molecules that are going to be involved in the reaction. And what happens? Maybe I'm like these chemical formulas for minerals and things where you have fractional numbers of atoms there, or am I just being confused? Is that just a probabilistic thing? You can't represent that here?
No.
Even with that second form.
Right, and I mean, even let's see. So the fractional coefficients, I feel like those are usually like in a unit cell. I might be wrong.
That's fractional occupancy,
right,
where in some parts that you've got different. I'm expressing myself terribly. The fractional occupancy means that in some unit cells, it's one type of atom, and in other unit cells, it's a different type of atom. Usually it's different metals like magnesium and
okay, all right, fine. All right, let's come back again
barium.
to the template reaction thing. Okay, so I think I more or less understand chemical reaction.
But there's
go ahead.
Well, so there's a futurized doc page for template reaction that has some sub values that I might want to get your eyes on.
Okay. You really like template reaction? I just don't like it because it doesn't talk about molecules and it doesn't talk about, and I worry that it's, I mean, it's just such a weird, you know, we got template reaction and reaction apply, which just seems very weird.
Well, if we
reaction apply, go ahead.
Oh, I'm sorry. I was just going to say, if you go with reaction transformation or chemical transformation, would it feel natural to have such as a catalyst or temperature requirements or heat or light requirements in that?
In chemical transformation?
Yes, because those things will accompany with a template, are part of a reaction.
What's wrong with that? Chemical transformation, what's wrong with having conditions in a chemical transformation?
No, I was just making sure that was okay.
No, I don't think there's a problem with that. But what would you call the reaction apply thing if we called that chemical transformation?
There's a proposed name somewhere there, molecule transformation and apply molecule transformation. One of the bullets in the left notebook.
Okay.
What about chemical reaction class?
I don't think that's right because it's not the same kind of thing. It's not a class of chemical reactions. It's a pattern. No, but
right. But if it were a called class, I would really want to test class membership, and I don't have that set up yet. Like to say is the chemical reaction an instance of this class or
but
something.
This is the implementation detail.
Yeah, that's an implementation detail. But what I'm claiming, Michael, is that this thing that you're currently calling template reaction is more like a pattern rule.
Yes.
Sure.
No question.
Sure.
Right.
I mean, is there a reason it couldn't be like reaction pattern? I mean, I guess it's not literally a pattern, but also maybe another problem to mention with template reaction is that template reaction doesn't integrate at all with the template apply, which if you do, template template star, all but a couple of the usages, all but some like obscure boxes work with template apply.
That is very true, and so I also feel hemmed in by the word pattern. So both template and pattern have specific meanings in Wolfram language, and my molecule pattern doesn't fully integrate with it. And
well,
but I do like the
string pattern is also not fully integrated.
So I like reaction pattern. If that's not offensive.
As opposed to chemical reaction pattern.
I think we should stay away from chemical in this context because the chemical could be an entity. It could be, we use it in other ways. And these patterns that we're talking about in the left-hand notebook are used with molecules specifically.
Specifically, yes.
Well, so you're suggesting reaction pattern reaction pattern doesn't sound terrible. And then what would be the apply version?
Apply reaction pattern.
Apply reaction pattern. Okay. All right. So that seems okay to me. Anybody object to those? So we'd be saying reaction pattern actually seems kind of nice to me. And reply reaction pattern would apply to would apply to the same stuff that you would say on the left-hand side of a chemical reaction. Is that a true statement?
Could we get away with just apply reaction rather than apply reaction pattern?
Possibly, yes.
That would be easier in an education environment.
All right.
It's certainly so. If you gave it a chemical reaction. So we could make it take a chemical reaction and then just require the arguments to come in to be verbatim, to match the...
Well, hold on. On the left-hand side of a chemical reaction better be the thing that is the second argument of an apply reaction.
Exactly.
Okay. So then I don't understand why you can't also, just like you've got a reaction pattern, why can't you also take a chemical reaction and apply it to the stuff that's on the left-hand side of a chemical reaction?
Right. No. So that's what I'm saying is that if it's reaction pattern and apply reaction, now that we're saying these, it should be able to take a chemical reaction in addition to a reaction pattern, but
yes,
it won't do. It's not. The things need to match verbatim. They need to match Q, not contains Q. Whereas
exactly
with a reaction pattern,
they're not right. Okay. So, all right. So let's see.
So there's a couple of subvalues that I think are important. Mainly the matching, to be able to tell, given a molecule, does this match any reactant?
Boy.
Does it match specifically? I'd like to know which reaction it matches.
Which reaction it matches? I mean, the fact is, putting a bunch of subvalues in here rather than having a bunch more actual functions. I mean, I don't know.
But they're very detailed.
Yeah, I know they're very detailed. So let's go through these a bit. So reactants, products, those are also supported in chemical reaction, correct?
Yes.
Reactants, products, and reactant counts
would be specific to chemical reaction and not to the reaction pattern.
Because reaction pattern, those are distinct objects on the left-hand side rather than countable.
Right.
Okay. Equation display, supported in reaction pattern. Why not?
Let's see, making a chemical formula for the things inside. A chemical formula generally won't represent the things inside a molecule pattern. Most of it would just be star or asterisk.
No, but we have those pictures in this thing here with R's and things. What's wrong with that?
Right. Okay. So equation display is, I mean, it's literally a row in that case. So it's not a visual.
Okay. But so this molecule pattern here, you're telling me I can put blanks in this. Is that right?
Yes.
So I can put a blank there, for example.
Yeah.
And that turned into a star in that picture.
Right. And I am interested in revamping enhancing how we visualize molecule patterns. Absolutely.
Well, I mean, what does the chemical literature have for that?
Generally, that's where those R groups show up.
Sure.
Yep.
Yes.
It would be an R.
So maybe what we want is some kind of stylized R. Maybe we want, an R with a colored background or something to indicate one of those. And if we did that, perhaps, I mean, with those R's and R primes and all that kind of thing. So what are we doing with the numbers here? What are we doing with those mappings? Why are we not worrying about saying which oxygen, in this drawing here? That's this business here.
Right.
Yeah, the thought was at least that the highlighting was more conveysive than, or informative, not conveysive, more informative than tacking the numbers onto the atomic symbol.
Although if you're printing it, you need something different.
What was that?
If you're printing it, it's no good to have interactive highlighting.
Yeah.
Yeah, that's
right.
Yeah.
But
so I think we want an option where you actually show the subscripts.
Yeah.
And so we kind of just assign them sequentially. In that case.
That's what I would do. Yeah.
Yeah.
But I think with what you're doing here, with that circle thing, which still needs to go through graphic design, but having that kind of circle thing as the indicator of a pattern object and putting an R inside it seems like a reasonable way to handle that star thing.
Right. I mean, so the only trouble I see, I mean, although maybe it's not that big of a trouble, but if you have 3 underscores, do you represent them as 3 R's? Because people can be forgiven for getting the impression that seeing 3 R's that it means specifically they're the same.
I understand. So, okay, so what are the alternatives? I mean, okay, if we wanted to go really exotic, we could have random colors in the backgrounds. We could have R's, but with a random color in the background, where each distinct R gets its own separate color.
Oh, it would be hard to tell. I have trouble distinguishing some colors.
Yeah.
No, well, so does everybody. But I mean, and it would give an indication that they're not the same.
In that case, that's where we would use the primes or numbering, like R1, R2, R3.
Yeah, and
that's what you prefer then.
I think we need primes or numbers. The colors might be helpful.
All right, fine, but this is an output form, so we can choose to, if there's a single R, it's just a single R. Otherwise, it's R1, R2, R3.
Yeah, but okay, so what about the reaction where the R's are the same? So
you mean I see where you're tracking. So your point is that you've got 2 different indices. You've got the index of the type of R it is, and you've got the index of which instance of a given R it is.
Yes, there is that also. Yeah,
right.
That's
what what you're basically telling me is that you have to use primes. That the indices 1, 2, 3 have to be which instance of the R it is, rather than which type of R it is. Am I making sense? So we probably need.
Yeah, you're making. Yeah.
So there are going to be cases where, like, so when creating a molecule pattern outside of a reaction, the user could want to call something R1, R2, or R prime. And so that I would love to nail down a syntax for them to be able to say. So in that case, they could do atom underscore, and then R group label goes to, and then some display form like R1, R prime, my fancy font.
Well, you're saying atom of underscore.
Mm-hmm.
Is it really an atom? Isn't it a functional group of some kind?
Well, no, I mean, in this object, it's an atom. And it represents, I mean, when you draw them, it's understood that, I mean, in this representation, that R might stand for anything else, but in this representation, it's just an R. Like in that notebook that you have over there, they're dummy atoms is what they're tend to be referred to as. And so dummy atom label would be a good key to use there.
Yeah, and when the R group is a functional group like a nitro or a phenyl or something like that, we're generally only interested in the atom that's bound to the reacting part of the reaction. All the rest of it gets carried along automatically, and we don't worry about specifying it.
Right, but so you're not worried about the fact that you're calling it an atom, even though it's got a big tail hanging off it.
We haven't worried about it. Maybe we should. But we haven't.
We've got plenty to worry about, I think.
No, I understand that. But I mean, my question is, do you really want these pattern objects to be called atoms in molecules, or should we call them instead something different, like whatever you're calling them,
So internally, I call them a query atom, but I've not tried to push that forward.
Yeah, and the other... the other thing we have to keep track of is if we have a bidentate R group, as in inorganic chemistry, where it's attached to through 2 different bonds to some other part, of the system that's reacting.
So how on earth do we represent that?
Well, no, I mean, so in that case, I mean, if you have an underscore in there and we decide to label a single underscore with an R, then if it has 2 bonds to it, then it would just show up that way. It wouldn't be, nothing special would need to be done.
Yeah, the bond list would take care of that.
I see. So in other words, so it's a faux atom. I don't like this. This is going to bite us somehow. It's going to bite us in stereochemistry. It's going to bite us somewhere. Because, an atom doesn't in and of itself. I mean, it is, okay, it has its orbitals hanging out, but it doesn't have the same kind of stereo, 3D structure that some, functional group would have. So go
I
ahead.
was going to ask, how would you feel if instead of forcing the head atom on the dummy atom, we make a dedicated head, like dummy atom or query atom, as mentioned earlier?
Well, yeah, but I think I think that the atom thing is a hack. The thing is not an atom. It is what is it officially called? That R thing, is it called?
Well, no, it's not officially called anything. R groups are kind of used all over the place. I don't think
they're colloquial. IUPAC doesn't define them. They're really just fragments that could have one molecule or one atom or multiple atoms, or as you often put it, a terminal vertex or a full subgraph.
Okay, but
and
so is it
thing,
in fact a molecule fragment?
Yes.
Fragment, yes.
So, I mean, and another thing, like, so you've got your main molecule that you're looking at, and it's got this R attached to it on one side. But then if you will often find in the paper that R is this other fragment, and the point where it was connected to the first molecule, you can label that with an R. So it's kind of, in that way, R can stand for just a half-formed bond, an attachment point.
Okay, let me make a generalized comment here, because I mean, in our effort of many years ago to sort of, computerize mathematics, right? There were many conventions that people had of, you can write, d2x by dx squared, right? But we're not going to follow that convention explicitly. We're just going to decide we have a derivative and you can do it twice. So I think, as we try and computerize chemistry, so to speak, we have to be aware of the fact we're not necessarily going to follow every by hand notational thing that people use. Fair?
Absolutely.
Yep.
So, I mean, but I think it's bothering me, this idea that we're going to have an atom. I think it's a mistake. I think if you have an atom that is a blank, it means a single atom that can be any, can be anything.
Mm-hmm. Or, that is what we're matching, though. Like, so when you match that against when you use it as a pattern and say, where is this? When we return back like the mapping of that template into the molecule,
yes,
or of the pattern into the molecule, we only assign one vertex to that.
I feel like it's right, because as Jay said, the piece of the molecule is an atom. There are stuff hanging off of it, but they can hang off on any other piece also, and they always get carried along.
I see what you're saying. So you're claiming that this pattern is sort of the backbone.
Exactly.
Yeah.
The thing represented is an atom, a single atom. It has kind of things attached to it, but that's a different story.
Fair enough. Okay, so then the thing that can be there can be alternatives, it can be a blank. The naming of that blank is what you were concerned about there, right? And the naming that you're proposing, go ahead.
Right, would be, so atom underscore, and then dummy atom label goes to, and then they could put in, subscript R.
Dummy atom is a horrible name. Can't we come up with something better?
So R group label, or atom label, I think is wrong, because we have
that's wrong.
atom, because that's wrong. Yeah.
Molecule fragment labels.
Well,
that's rigorous. It's awful long to type, though.
Yeah, it's awfully long.
Yes.
We can maybe skip the molecule, because already it is within a couple molecules.
Could it just be a label? Label goes to?
No.
Or is that too?
No, too short.
So wait a minute. This is, what else is in atom? What other stuff is inside atom?
So atom, the first argument is your atomic symbol, or the blank here, and then you list of rules. You can tell it the formal charge, mass number, the
okay, those are strings.
Electron count. Yeah,
those are strings. Well, then why don't we just say display name? I don't know, that way if you put in display name, then you could, change your random carbon to have something, to be a display name that is a carbon with a red circle around it or something.
No, that works for me.
Actually, is it,
Well,
or label or something?
Would that be a tag?
I was thinking it's not really a name.
Yeah, fine. All right, okay.
Display label then.
What other examples do we have of this? I mean, like for example, we have vertex label is an option in graph.
Right.
But,
so in graph, you have like vertex rendering function or something. So if you wanted the vertex to render as the letter R, even though the vertex is
well, you just say vertex
expression.
label. You just say vertex label, and then you give. But is a question actually for Charles or anybody else is in the vertex list. Is there a way of saying right in the vertex list that I want this vertex to be, its actual name is foo, but it is to be displayed as a red bar?
It's annotation.
Which you can give in the vertex list.
Yes. When you create the graph.
I see.
If
so
you
that's it, but it's option. That's an option which is being added in an annotation there.
Effectively, yeah, it ends up going into the vertex label list.
Right.
It's just like vertex style.
I think here what we need to do well, okay, so what should we call this? This is atom label, or no, it isn't an atom. It's really
So I would like display label, although I could also be happy with display name.
Display label seems better than display name.
Okay.
We use label for vertex label. Oh, no, we don't. Vertex label is a label outside of the vertex itself.
Yes, that's right.
I think it's display name, although Michael seemed to have an objection to display name.
It seems, why is it more a name than a label? For me, it's a label, not a name.
Okay, tell me, the reason I'm saying it's okay, the question is, a label in a graph is something which is shown to describe the node, but the node is drawn however the node is drawn, and then it's got a side label that says, A or something, right? But the node itself is drawn as a gray dot or something. And
right,
most of the labels that we have are off, are off object.
I see.
And so is the atom label. Like atom label was added recently, and I mean it's exactly equivalent to vertex labels.
So it's an off object.
I had originally, like within the group, proposed that you should just be able to say what the atomic symbol is. Like say atomic symbol goes to R, but that is not quite right, because that atomic symbol is something that really means something, and you can't just say carbon has an atomic symbol at the end.
It's more like we want an atom rendering function.
It's not just the label, right? It's also how you put these connectors to the rest. I mean, would one call? I mean, what kind of, you said atom underscore would use for R groups? I mean, what kind of index do you then use for bonds? Is it always one?
Well, no, I mean just wherever it shows up in the atom list.
Right.
Yeah. And the other thing is, these R groups, there are conventions how to display them, right? In nature, it's always superscript. It's never subscript.
Right, but there's, I mean, from my research, there's lots of conventions. I mean, it would be like we could pick one, but
so the reason
they're not always.
Look, display name seems harmless here.
Absolutely.
And I think then.
So a new symbol for this, yeah?
No, it's a string. It's one. It's
okay,
like one of these,
good,
like the formal charge and so on.
Good.
All right. I need to wrap up here, but was there anything else that we need to? Oh yeah, you were wanting to ask about those weird things.
Right. So they're very data structure like. They are in that they are subvalues that take arguments
Okay, what are
I'm
they
a
doing
fan
again?
of them, but,
Reactant match Q. This is really deep in the entrails of this particular molecular
Yes.
goat.
But it's needed for proper programmatic dealing with the things.
Right.
Reactant match Q returns true if molecule matches any reactant in the reaction. I don't know. I don't have a horror. I'm not horrified.
Excellent.
The nth reactant pattern matches the nth. That's so freaking weird.
The alternative is that we have dedicated functions for all of these.
Well, I mean, we can always go to
practical.
that. Yeah, we can always go to something more like that later. I mean, I feel like. By the way, does anybody know what Emerald is doing with these reactions? Do they have a representation of these things?
They do.
Yeah, but we've never seen details, have we, Jason?
No.
Well, why don't you look at their documentation? It's online. We can ask them. I think we're going to do a session with the Emerald folk hopefully early next week, where we're actually going to do some chemistry. Hopefully, like we're actually going to,
do an HPLC or what they
yes, hopefully. I mean, we'll have to get set up. I think we need to get all the account information and so on set up. Maybe we'll send them a sample that we can do this on. And then maybe we can. I don't know how real time it can be done.
I had sent Nathaniel some stuff a little bit earlier today about the Diels-Alder network that we've been talking about. And
okay, cool. So you think
to send on to
it's
Brian.
Realistic to? I mean, is it plausible? I mean, I don't have any sense of this. How long do those reactions take? Is it like minutes, or is it like?
Yes, they're very fast. Some of them, no heat at all at room temperature, and it's over very quickly quantitatively.
But what does very quickly mean? Does it mean a minute, or does it mean
minutes? Yeah.
Huh. And so then it will have produced whatever it's going to produce, and that just sits there, and then you can analyze it.
Yeah.
Wow.
I'm trying to get as much background on these different things as I can to know what's feasible and what's not.
Okay. And so then you would expect that. I mean, the analysis, like an HPLC thing, how long does that take?
Those will be longer.
Like hours or what?
I
mean,
I'm not sure. It's HPLC was new when I was still in the lab, and the things have probably changed a lot. Brian would be able to give you a much better idea of what contemporary HPLC is like. Okay.
But I mean, I just don't. I mean, like doing chromatography with filter paper, it takes many minutes.
Oh yeah, that does. It takes forever for the solvent to creep up filter paper to do that separation.
Yeah.
But an HPLC column is not filter paper.
No,
no.
Pressure is on your side.
Yes. They
pushing it to the column.
Okay, fair enough.
The HP is either high performance or high pressure, depending on what you're talking about.
Depending on who you ask.
Yeah.
Okay, fair enough. Well, okay, so this will be, but it will be good if, I mean, in a perfect world, right? Just like we can take, a 3D geometry and send it to a printer, it would be super cool to be able to take chemistry and send it to Emerald.
Absolutely.
Sure.
I mean, and
a credit card.
Well,
yeah.
Same with 3D printing, right?
Well, yeah, that's true. That's true.
I think they restrict 3D printing your own credit card.
No.
That's a different subject altogether, Jason.
Very good, Jason. Very good.
We have to. Emerald, no doubt, has things where if you give it an explosive reaction, they will try and detect that.
Yeah.
Sandbox mode.
Yeah, but okay, it's more than Emerald. We have to bring in, Sigma Aldrich or whatever to get starting materials and so on.
And can we reference that if we wanted to reference the Sigma Aldrich? Do they have do they use CAS numbers or what do they use?
Yes, they have a catalog. They have a whole catalog of stuff.
Yeah, they would use the catalog from Sigma Aldrich. Use the catalog numbers.
But then can we transform, if you have an entity, a chemical entity in our system, can we get the Sigma-Aldrich catalog number?
Probably. I don't know if Jason has it hooked up, but I'm sure it's feasible.
But so that's a reasonable API. I mean, it's a reasonable thing to, I mean, you know, if we're actually getting real here so that we can actually start imagining, you know, I mean, look, if we can get the Diels-Alder thing to work, then we can go all the way from symbolic chemical reaction to actual, you know, measuring those things. And then it starts to really matter that we can do things like transform to a chemical catalog and so on.
Yeah. I don't know if Stephen is aware of this, but Sigma-Aldrich also provides custom synthesis services. So you ask them what to make, optionally how to make it, and they'll do it for you for a stiff fee. For a stiff fee.
Yeah, I'm sure that that's a very different process. I think that's presumably humans doing things. That's not
it would be. It would be. That was that used to be Aldrich's Bayer catalog for some of that stuff.
Right.
But it wouldn't be just run this reaction and tell me what came out. It's you know, please make this particular compound, and they will figure out what the appropriate starting material is and reactions to use and try to do it, you know, cost effectively, so they make a profit.
Right, but that's surely an expensive and long. I mean, that's very different story from what we're talking about here, where we're.
It is. It is. Yeah.
Okay. Well, very good. All right. Anything else that we need to cover right now?
We're good.
Just one totally random side remark, because I was reading a paper about this recently. So the detailed influence of indistinguishably of the atoms in chemical reaction is a very complicated story, and it's not fully understood these days.
And that has to do with this continual measurement nonsense in chemistry.
Exactly. It has to do with measurement. It's basically post Born-Oppenheim.
Yeah. So just explain this to me, because I mean, usually when you exchange, you know, when you have fermions, for example, you have a -1 phase. When you have, you know, you have a thing where the two fermions are exchanged, there's a -1 phase. But you're telling me when two fermionic atoms are exchanged, there is not a -1 phase in chemistry.
No, I think kind of like even the meaning of what did exchange here becomes much more fuzzy in the environment around.
I see.
Like there's the other things around. The other things around basically are with respect to the two things, like apparatus that measures the two things.
Hold on a second. So destructive interference, does it happen in chemistry? In other words, if you did the chemical two-slit experiment, where the carbon atom can either go that way or that way, are you telling me that basically you would not see, there's this question, would you see destructive interference?
With two individual carbons, definitely. I think has been even done with buckyballs.
Yeah.
Okay, but that's not what I'm asking. I'm asking in those things, you're saying it will, if they're individual and they're not bound to other things, they're not part of molecules, you will see it. But if those buckyballs had trailing crud because they were part of a molecule, you're saying you wouldn't see it. Is that right?
Naively, yes.
Right.
And so because in a sense, the trailing tail of molecule is a continual measurer.
Yes, exactly.
I'd like to understand this better. This is telling one something about, I mean, this idea of microscopic, you know, sort of nanoperception measurement is sort of interesting, because that is beginning to take apart the monolithic concept of measurement. I mean, is that a fair, I mean, in other words, by saying in chemistry, it is no longer the case that, I mean, okay.
No, I think it makes the difference between what's technically called the pre-measurement, where you get into an interference term between apparatus in this system and this plus prime plus 2 prime. This is very easy still on the microscopic level if you have part of a molecule and the rest. But then there is normally no amplification in the macroscopic irreversible step if you are at the individual.
Indeed. Yeah, if you're an individual atom, an individual molecule, so to speak. Yeah.
Yeah.
Right. And I see, but the point is, there isn't amplification, but if you have a chemical reaction, you have a very large number of molecules, you can then do, what is the analog then? I mean,
I think that if you do this in cold atoms with 12 in your little ball, and you let them come very carefully, you get all kinds of interference. But if you have it in a real environment where the other ones come with collisions, you immediately decohere and become classical.
This deserves further understanding. I mean, I think it's interesting. I mean, I think, and the decoherence time is presumably comparable to the collision times, or what? In other words, is it the case? Because that is basically thermalization, very directly so. I mean, just like in a measurement, you say, I'm going to do amplification, and when I do amplification, I'm basically going to make this giant cascade, and I want that cascade to have certain thermodynamic properties so that I can, so it doesn't interfere with a different version of the cascade. In this case, when you're having actual molecules colliding, it's the most direct form of thermalization, if I understand correctly.
Yes and no. It depends now if your collisions are elastic or inelastic.
Elastic.
Yeah, but they're presumably elastic most of the time. I mean, unless they're reactions, they're elastic collisions. And what's wrong with, I mean, elastic collisions still lead to thermalization.
No, I think that's generically, unfortunately, not correct.
Really?
No.
Why? I mean, they randomize the momenta of the molecules, the momentum vectors.
Yes, like with sufficiently many, but not with a few.
How many do you need?
I don't know, maybe thousands or something like this.
That is a very interesting claim, heavily related to this whole subchemistry discussion that we've been having. Because, that relates to, if you have a little reaction network that involves, let's say it doesn't thermalize for, you've got this ring of 5 reactions, of 5 collisions happening. You're claiming, anyway, more to be understood. We got to wrap up here.
This is like this persistent currents in cold atoms.
Explain.
Like in a superconductor, like you can bring a bunch of atoms in a state that will flow forever.
Sure.
Yeah.
A bunch of atoms as opposed to electrons. You're saying.
Yeah, but they interact through the electrons.
Okay. And why? I see. Okay. Because it's a single quantum state. You're claiming that.
Yes.
And so even though there are multiple. Right. The question is, I mean, this is the question is, how many connections do you need to the outside world? Okay. Anyway, more to be thought about at a different time.
Yep.
That's very interesting. All right. Great stuff. Talk to you all soon.
Thanks.